Now we're going to start with one of the more fun sections in this chapter, 17.5, Batteries and Fuel Cells. Here we're going to describe the electrochemistry associated with several common batteries and distinguish the operation of a fuel cell from that of a battery. This section is more or less talking about different types of batteries. It's kind of cool. So a battery is a galvanic cell that has been designed and constructed for its use as a source of electrical power for specific applications. So, like I said at the beginning, galvanic cells are batteries. Batteries are galvanic cells. We have primary cells, which are batteries designed for single-use applications and cannot be recharged. And then there are secondary cells that we can recharge using some type of external power. So, one of the more crude first versions of batteries are the Daniell cells. And so this is from a 1904 journal publication. And then you can see the simplified cell on the right. It used a porous clay pot to both contain one half of the cell's content and to serve as a salt bridge to the other half cell. So this paved the way for single-use batteries. So first we have dry cell batteries, and these use zinc, a zinc can as both the container and anode, it's the negative terminal, and graphite as the cathode or positive terminal. So that zinc can is filled with, and then the graphite cathode is immersed in an electrolyte paste that has manganese 4 oxide, zinc 2 chloride, ammonium chloride, and water. So you have this paste in there, and that's what the cathode, that graphite cathode, it's kind of a rod that's immersed in it. And then these have various sizes, D cell, C cell, AA, AAA, sound familiar? But they all have the same potential of 1.5 volts. So where these sizes come into play, what it is the larger batteries have more reactance in them, so they can transfer greater amounts of charge, but the voltage is the same. So what's happening is you have your anode reaction, which is the zinc solid going to zinc 2 plus and 2 electrons. And then you reduce the manganese. That's your reduction reaction. You see there. And then you put it together and you get your overall reaction. And with an overall potential of the cell at about 1.5 volts. So this is a schematic showing a dry cell battery. You've got your metal top cover, it's got some insulator, your seal to keep everything together, and your zinc and carbon, and separators, your paste, and your metal bottom cover. So then we also have alkaline batteries. Now these are the ones that we see more nowadays. So these were designed in the 1950s to improve on the performance of dry cells. So they use alkaline, meaning basic, electrolytes, so usually potassium hydroxide, and they produce 3 to 5 times the energy of a zinc carbon dry cell. But one thing with these is they're prone to leaking potassium hydroxide and should not be stored long-term in devices. So, battery acid we talk about, which that is actually from like car batteries. So if you pull out an old battery and it's covered in stuff, it's actually not sulfuric acid, but it's potassium hydroxide, which is still, you don't want to get on your skin. Hydroxides turn your skin literally to soap. Fun times. So those should be disposed of. As a matter of fact, I'm actually a little late making my recordings because the power went out in my house, and I was going to set up one of my flashlights just so I could look around, and when I went to put the batteries in, I noticed a couple of them were had burst, and there was that battery crap on the outside, so I had to throw them away. I washed my hands properly, so that was fun. And they weren't even that old, but it can happen. So it's a good thing they weren't in the flashlight, though, because when that happens, when it leaks, that can damage the inside electronic components. So if you need to store something long term that has batteries in it, don't store the batteries in it, because that leakage can damage your product. Also, do not try to recharge them. Most of them have a warning that says, don't recharge. And the reason is you can actually cause the battery itself to rupture, and then that potassium hydroxide can leak. So you have the zinc anode, but it is then reacting with the hydroxide from the potassium hydroxide. And then your cathode, again, is manganese. So it's very similar to the dry cell, but improved. So, and then here's their schematic, very similar to the dry cell battery, but this is what we have nowadays. The next part is, sorry, something started playing in my ear. Rechargeable which are secondary batteries. So the first type is the nickel cadmium. And so you have a nickel plated cathode and a cadmium plated anode and a potassium hydroxide electrode. And then the way it's designed is you have these positive and negative plated plates that are separated, and then they're rolled together in the case. So it's called a jelly roll design. Sounds delicious. Please don't eat them. These can be recharged about 1,000 times, but they have to be disposed of properly because cadmium is a toxic heavy metal. So you can see the reaction there for the anode, the cathode, and the overall cell reaction. And the potential of the cell is about 1.2 volts. And so here's that nickel cadmium battery with the jelly roll. So a lot of rechargeable AA's and AAA's tend to be nickel cadmium. And so you can just see their design here. Then we have lithium ion batteries. So these are getting more and more popular. These tend to be what are used in portable electronic devices. And we're seeing more of them in rechargeable like AA's and AAA's. The reactions are down below, and then they have varying stoichiometry of the cell. So this is what allows variation in cell voltages. So if you're looking at the reaction, you see like that X Li plus and X electrons. So since we can vary that X, we can vary the stoichiometry. It's generally, though, no more than 0.5, and that gives a cell voltage around 3.7 volts. So a bit higher voltage. These are also lighter weight and have a larger amount of current than comparably sized batteries. They make a nearly constant voltage, and then they slowly lose their charge when stored. So you turn your phone off, for instance, you're not using it, and the charge of your phone doesn't go down all that fast. I mean, one of my favorite examples, back in the day when I was in high school, so this was, well, actually I was in junior high when I got the phone, so this was 2002 or 2003, actually, I think, and I had a Nokia. It was Nokia's brick phone. It had a color screen. I was super cool. This thing was indestructible. And then a couple of years later in high school, I had gotten my first flip phone that died within a year. I did nothing wrong. It just died. And that was back in the day, Motorola was awful. It was a Motorola. So I had to go back to using my good old brick Nokia. This thing had been turned off and stored for, at that point, 3 years, I want to say. And out of curiosity, I hit the power button to see if it would even turn on. And sure enough, that sucker turned on. So there's that lithium ion battery and Nokia. So this is just a schematic kind of showing you the charge versus discharge of lithium ion batteries. You have charge flowing between the electrodes as the lithium ions are moving between the anode and the cathode. We have lead acid batteries, and these are what are generally used in automobiles because they're very inexpensive but capable of producing the high current that you need to start your car. And then each cell itself produces about 2 volts. So to make a 12-volt car battery, it has 6 cells that are connected in series. So then that gives you 6 times 2, total of 12 volts. Sulfuric acid is the electrolyte, and it's caustic. I mean, it's a strong acid. So if you remember when we were talking about acids and bases, it's one of those strong ones. So proper disposal of these batteries is very important. It's also important to watch for leaks because sulfuric acid is bad. So that is when we talk about battery acid, we're talking about battery acid that's coming from a car battery or lead acid battery. So there's a schematic showing you that lead acid car battery. And lastly, we have fuel cells. So these are galvanic cells that uses either hydrogen or methane that are fed into the cell along with an oxidant. And what's cool about fuel cells is they're actually much more efficient than internal combustion engines. So they tend to have an efficiency of 50 to 70%, whereas internal combustion engines tend to be 20 to 25%. So fuel cell vehicles and stuff are amazing. Like, I would love to have a fuel cell vehicle, but unfortunately in the high desert, we don't have any fuel cell charging refueling stations. I think the closest is probably Irvine. But oh, they're so cool and I want one. I'm hoping the technology continues to advance. Hydrogen fuel cells are used for extended space missions right now and some personal vehicles. So if you ever see a Toyota Mirai on the road, for instance, that is a fuel cell vehicle. But this technology is still evolving, so I'm very much hoping that it continues to evolve and becomes much more affordable. So these tend to give a potential cell of 1.2 volts per little cell. And then here's a schematic showing you the oxygen from the air is reacting with hydrogen, producing water and electricity, so giving you your energy for your car.